In the first part of this problem, we have to check if mean value theorem can be applied to this function f of x equals x over x minus 5 in the closed interval 1 comma 4. So let's see how to determine that. Here let's go through the review of this mean value theorem, which states that if f of x is continuous on the closed interval a comma b and f of x is differentiable on the open interval a comma b, then we have f prime of c equals f of b minus f of a over b minus a. So we have to first determine if the mean value theorem can be applied to this function. For that, let's check these two conditions first. So if these two conditions are met, then we can say that this equation is true. So here we have this function f of x equals x over x minus 5, which is basically a rational function in x, and all rational functions in x are continuous on their interval, on their domain of the function. So the domain of this function is 1 comma 5. This rational function is defined and continuous in this domain, except when the denominator equals 0. Here the denominator is x minus 5. So if we let this denominator equals 0, we see that we get x equal to 5. That is, when x equal to 5, the function is not continuous. So for x should not be 5. So we can clearly see that the domain of this function is 1 to 4, which means the function is continuous on this closed interval 1 comma 4. And same goes with the next verification, that is f of x is differentiable on the open interval a comma b. As such, this is once again a rational function. It is differentiable for all values of x defined in this domain, except when x equal to 5. But x equal to 5 is not the domain of this function. So we can say that this function is differentiable on the open interval 1 comma 4. And so therefore we can now say that mean value theorem can be applied to this function. And this means we can consider this equation, that is, this equation must be true. That is, f prime of c equals f of b minus f of a all over b minus a. So first let's determine this f prime of c. This is basically the derivative of the function when x equal to c. So I'm going to use the function f of x, and this is given by x over x minus 5. So let's find the derivative of this function by applying the quotient rule of differentiation to differentiate this function. So we get f prime of x, and this equals, I consider the denominator polynomial, that is x minus 5, then multiply with the derivative of x, which is 1, and then I put minus. Now I consider the numerator function, that is x, and then multiply with the derivative of x minus 5, which is also 1, and this is over the denominator square, that is x minus 5 quantity square. So this we have done according to the quotient rule of derivatives. So let's simplify this. We have f prime of x, and this equals x minus 5 times 1 is x minus 5, and here we have negative x times 1 is negative x. This is over x minus 5 quantity square. And so this gives this positive x and negative x gets cancelled. We are left with negative 5 over x minus 5 quantity square. So basically f prime of x equal to this expression. Now we have to find f prime of c. So let's replace x by c into this expression. And thus we get f prime of c equals negative 5 over x minus, I'm sorry, we have to replace x by c. So the denominator becomes c minus 5 quantity square. And now that we have determined this f prime of c, we can substitute into this equation. So let's put a line over here. F prime of c equals negative 5 divided by c minus 5. quantity square, and this equals f of b. Let's identify the a and b. This one is a, and 4 is b. So therefore here we can write f of b. B is 4, so it is f of 4 minus a is 1. So it is f of 1 divided by b minus a, that is 4 minus 1. Let's simplify the right side. So f of 4 is basically, we have to replace x by 4 into the function f of x, which means we will get 4 divided by 4 minus 5, and minus f of 1, we replace x by 1 in f of x, so we get 1 divided by 1 minus 5, and this is all over 4 minus 1 is 3, and this side we have negative 5 over c minus 5 quantity square. Let's simplify the right side expression. So this gives 4 divided by 4 minus 5. 4 minus 5 is negative 1. So I'm going to write down this as negative 4 by 1. And this is 1 divided by 1 minus 5. 1 minus 5 is negative 4. So we already have a negative. So therefore this becomes positive, and this is 1/4. This one divided by 3. Let's simplify the numerator fraction. So here the common denominator is 4, and then this has to be multiplied by 4. So it becomes negative 16. And this numerator 1 is multiplied with 1, so it becomes 1. So this is how we simplify the numerator fraction. This one divided by 3. And so when we simplify this numerator expression, negative 16 plus 1 is negative 15 divided by 4, and then we have to divide by 3, so I can write down this as multiplied by 1 by 3. Now we do some cancellation here. We have negative 15 divided by 3 is negative 4, sorry, negative 5, so it is negative 5/4. And so on the left side we have negative 5 divided by c minus 5 quantity square. We'll write down here negative 5 divided by c minus 5 quantity square. We divide both sides by negative 5, and when we do that, we will get 1 by c minus 5 quantity square, and on the right side we get this equals 1 by 4. And so we can cross multiply and solve for c minus 5 quantity square, and this gives c minus 5 quantity square equals 4. We now take a square root on both sides. So here we get c minus 5 equals square root of 4 is plus minus 2. We solve for c from this equation, that is c minus 5 equals 2, or we have c minus 5 equals negative 2. And so from here we get c equals 5 plus 2, which is 7. And from here we get c equals 5 minus 2, which is 3. And we have to verify which c belongs to this function, or which one satisfies this mean value theorem. Considering c equal to 7, the interval or the closed interval of this function is 1 comma 4. This 7 does not lie in between 1 comma 4. However, this c equal to 3, that is when x equal to 3, it lies between this 1 comma 4. So therefore we have consider, or we have determined that c equal to 3 is the one which lies in this closed interval, which satisfies the mean value theorem.